So let's see, we've got our introduction to Galois theory over with now, and so now we're going to start getting deeper into the subject. Now, I left off in kind of an awkward spot last time, so let me just sort of remind you. So let's say like this. So recall, if we have G is a subset of the group of automorphisms of some field L, and M is a subfield of capital L, then there's this set which I write L raised to the G, and this is really just standard notation, right? It's the set of all functions from G into L. This is not group theory or anything, this is just a set. But it turns out that under the appropriate operations, this is a vector space over any subfield, right? So where the scalars can come from any M here. So so this is a vector space, over M, right? Where the operation, so there's going to be, right, if F is a function from G to L, we can look at alpha F, where alpha comes from M, and then F of, who do I want? I'm applying it to G, so let's say sigma, right? And so this is just alpha. Did I use a sigma? Oh, yeah, that's fine. Sigma. Yeah, fine. Alpha F of sigma, and I was just looking at my notes, and really what I used was a little a. But no, this is good. Okay, and then also, so F plus G applied to sigma is just going to be F of sigma plus G of sigma. Right, so those are our operations. I'm just going to look at, see what symbol did I use last time. Oh, I used a little S last time, I guess. So whatever, this is fine. It's just a symbol. Each of these, this sigma here, it's coming from our group, right? It's a function, and who's the domain? It's the set of G, so I'm just thinking of sigma as an element of G. Anyways, so here's the two cases that we're going to be interested in is when M is either equal to L or when it's equal to phi of G. We will be interested in the cases. So this is true for any subfield, but we'll be interested in the cases M equals L and M equals the fixed field phi of G. So, and then there's a little bit of notation, right? So for each little lambda in L, we can define a function t of lambda going from G to L by t lambda of, and I think here I did use sigma, didn't I? Yeah, sigma equals sigma of lambda. And so what we have here, this is a function from G into L. There's the formula for it. Fine. And so, yeah, all this means is, or this notation here, we know that t of lambda then is an element of L raised to the G, right? The set of functions from G to L. All right, so now our goal is to prove this theorem. So this is theorem 5.3. And so I'm going to write down the first bit, and then I'm going to say some words before I write down the rest of it. So let's let G be a subgroup of L, and capital B a subset of L. Now, this theorem has 3 parts to it, and they're all linear algebra statements. They're all statements about linear independence. And so they're going to look a little bit odd. I mean, in fact, the reason it can't be. It's not clear why I'm even introducing this particular vector space. And so what we just have to do is accept, right, we're going to need this theorem for the next theorem that we're going to prove. And this theorem will be a linear algebra thing. And so I guess, what am I trying to say? Roll with it. Right? We're just, I can't think of the right words here. I'm trying to say the power of linear algebra, right? Linear algebra is a tool that allows us to do all kinds of stuff. And so what we're seeing right here is we're going to get a sort of technical looking linear algebra theorem that will then allow us to do some Galois theory type stuff. So this is purely a linear algebra theorem right here. So the following are equivalent. There's going to be 3 parts here. So the first one is that the set B is phi of G linearly independent. So sitting inside, this is happening in L here. Right, so viewing, we've got L, it's an extension of phi of G, and so we've got a vector space, right, where we use scalars from phi of G. The second part is that the set of all functions of the form, say T beta, where beta runs through this set, or runs through all of capital B, is... and I want this one to be phi G. Yep. Phi of G linearly independent. But now notice, this is happening not in L, but this is happening in L raised to the G. Right? So there's this connection between linear independence in L and linear independence of the functions from G to L. And then the last part is that the set TB, or T of, I guess that's a beta, T of beta, where beta runs through all of B, is L linearly independent. And once again, this is happening in L to the G. So that's a little curious here. Notice that we're working with part 2 is working with scalars in phi G in the fixed field, and then part 3 is working with all possible scalars, everybody in L. Like I said, this doesn't appear to really fit with all the Galois theory stuff we've been doing. Other than, of course, I mean, there's this and there's this. But overall, this is purely a linear algebra theorem, and it's going to be really just a linear algebra proof, right? I mean, we're just going to look at linear combinations. So, for the proof, so we need to complete a cycle. And first, let's get the easy one out of the way. That's the one I want? Yeah, 3 implies 2. This is automatic. Right? If you can't form a non-trivial linear combination using coefficients in L, then you definitely can't do it by reducing the number of coefficients, or the collection of coefficients that you're allowed to use. Scalars, I should be saying, instead of coefficients, right? So, yeah, if you can't do it using L scalars, then you certainly can't do it using phi of G scalars. Okay, so there's that part. So now we're going to do 2 implies 1. And this is just really going to be a Math 306 kind of proof. So 2 implies 1 is what we want to do. So what do I want to do? I'm going to assume that we've got linear independence, and then we want to show that B is linearly independent. So I want to take a linear combination, set it equal to 0, and show that all the coefficients have to equal 0. So, so let's let beta 1 up through beta n in B, and alpha 1 up through alpha n be in 5G, such that alpha 1 beta 1 plus dot 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 plus alpha n beta n equals 0. And what we need to do is show that all these alphas are equal to 0. Now, if we take some element of G, so if sigma's in G, then I need to write it over here. Okay, so what do we have? 0 is equal to, so what I'm going to do, we know that this is 0 right here. This is an element of L. And so I can apply sigma to that element of L. Right? Sigma is an automorphism of L. So what we have is 0 equals sigma of this linear combination alpha 1 beta 1 dot 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 plus alpha n beta n. And then we know that sigma, it's a homomorphism, right? So this is going to be a sigma alpha 1, sigma beta 1, plus dot dot dot, plus sigma alpha n, sigma beta n. Now let's see, these alphas came from phi of G, which means that they are fixed by every element of G. So, for example, sigma of alpha 1 has to equal alpha 1. Sigma of alpha 2 equals alpha 2, and so on. So this is alpha 1, sigma beta 1, plus dot dot dot, plus alpha n, sigma beta n. And then, oh, right. So now I want to use, remember that tau, or the capital T notation. This is equal to alpha 1 T beta 1 of sigma plus dot 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 plus alpha n T beta n of sigma. And then using the fact that these are linear maps, this is equal to alpha 1 T beta 1 plus dot 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 alpha n T beta n, all of that applied to sigma. Okay, now, so what do we have? We have that this function right here, right? Think this is living in the vector space L raised to the G. So this function gives an output of 0 when we plug sigma in. And we chose sigma at random. There's nothing special here. So this actually holds for all sigma in G. Right? So since this holds for all sigma in G, we conclude, right? So if you plug everything in the domain and you get 0, that means you're the 0 function. And so that tells us that this right here is equal to 0, the stuff inside the parentheses. So we conclude that alpha 1 T beta 1 plus dot 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 plus alpha n T beta n equals 0. Right, so it's the 0 mapping. But remember now, the collection of T of betas is a linearly independent set. So since the set T beta, beta runs through B, is linearly independent, we have, so that forces then all of these, oh shoot, yeah, sorry, that forces all of these alphas to equal 0. So we have each alpha I equal to 0. And so what does that tell us then? It tells us that our original set that we're looking at, our set B, is linearly independent. So therefore, capital B is linearly independent. Okay, so that's 2 implies 1. Now we want to do 1 implies, let me just, is linearly independent. Remember who our scalars were. Our scalars were coming from phi of g. So it's linearly independent over phi of g. Okay, so that was 2 implies 1. Now we need to do 1 implies 3. All right, so now let's assume that B is a linearly independent. And I guess I really need to be careful here. It's, well, it's linearly independent over phi of g. And now what we need to do is show that this set right here is linearly independent over L, right? So this is, okay, so we'll say, and suppose that, and we're actually going to do this by contradiction. So suppose that the set T of beta, where beta is in B, is linearly dependent when we use scalars coming from all of L. Okay, so then what does that mean? So then there exist non-zero scalars, so these will be alpha 1 up through alpha n in L, and let's say beta 1 up through beta n in capital B, such that alpha 1 beta 1 plus dot 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 plus alpha n beta n is equal to 0. All right, so we have a non-trivial linear combination adding up to 0. Why am I not happy with what I just wrote here? This should, sorry, I know why. Because these should be T of B. Sorry, so this should be alpha T beta 1 plus dot 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 plus alpha n T beta n equal to 0. Right, because we're supposing this thing is linearly dependent. Okay, and by the way, what is this saying? Remember, this is happening, this is a set of functions here. This is a linear combination of functions, which means it is a function from G to L. And so what we're saying is that this is the 0 function. Now, we can choose n to be minimal. This is sort of the trick. This will come back right at the point of contradiction. This minimality is going to show up. So we can choose n to be minimal. Now, what that means is if you take any collection of betas that has fewer than n elements, then that set is going to be linearly independent, right? You won't be able to come up with a non-trivial linear combination that adds up to 0, right? So we can choose n to be minimal. And so, let's say it like this, so that t beta 1 up through t beta n is the smallest linearly, and do I want to, yeah, smallest linearly dependent subset of L, G, and remember here we're using coefficients from L, so with respect to L. Okay, fine. So what that means is that, remember, this is a function. This is a function from G to L, so that means that every time that I take an element from G, let's call it sigma, and plug it in here, I'm going to get an output of 0. So then, for all sigma in G, we have alpha 1 t beta 1 plus dot 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 alpha n t beta n applied to sigma equals 0. So now I'm going to make use of the definition of this t sub beta, and so we can say, so for all sigma in G, alpha 1 sigma beta 1, alpha 1 sigma beta 1 plus dot 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 alpha n sigma beta n, that's equal to 0. And I'm going to need this equation in a second, so I'm going to label that one star, and I'm going to have a double star in just a second. So now what am I going to do? I'm going to pick a couple of elements. So this part of the proof is kind of intricate here. So let's pick I'm going to pick a sigma and a tau in capital G. Then, okay, so remember this holds for all sigmas, in particular, all sigmas in G, are all elements of G. In particular, it holds for the next element of G that I'm about to write down in place of sigma here, and that is going to be tau inverse sigma. So then, alpha 1 tau inverse sigma beta 1 plus dot 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 plus alpha n tau inverse sigma beta n equals 0, and this one I want to label let me not yet. Let me hit it with tau first. So applying tau, we get, so I'm going to apply tau to both sides of this equation right here. And so this will give me tau of alpha 1, sigma of beta 1, plus dot 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 tau of alpha n, sigma beta n equals 0. And this one I'm going to label double star. Okay. So now I'm going to multiply my star equation by tau of alpha 1. So let's write it like this. So multiplying equation star by tau of alpha 1 and multiplying double star by, I think it's just alpha 1. Yeah, by alpha 1, and then subtracting by alpha 1, and then subtracting, and let's just actually write out all the steps there. Okay, so I hit the first equation by tau alpha 1. So it's going to be tau alpha 1, who was it? Alpha 1, sigma beta 1, right? Sigma beta 1. Sigma beta 1 plus dot plus tau alpha 1 alpha n sigma beta n. That one's equal to 0. And then I also multiply double star by alpha 1. So that'll be an alpha 1 tau of alpha 1 sigma beta 1 plus dot plus alpha 1 tau alpha n sigma beta n. That one's also equal to 0, and then we're going to subtract. Now, okay, what's happening here? Well, notice in the first spot that's going to go away, but everything else is going to remain, right? And so what did we do? We just created. Remember, we had that minimality condition. So this is going to throw off minimality, and we'll see that in a second. Okay, so let's write this down carefully. When we subtract, what we'll get is tau of alpha 1. Make sure I write it down correctly. Alpha 2 minus alpha 1 tau alpha 2. Right, alpha 1 tau alpha 2 sigma of beta 2, right? The first terms right here cancel out, and then the rest of them subtract, and I'm just factoring these as we go. And so the last one is going to be tau alpha 1 alpha n minus alpha 1 tau alpha n, alpha 1 tau alpha n times sigma beta 2, and that's equal to 0. Right, okay, so next, sorry, I gotta be careful here. So now I want to look at the definition of tau of each of the beta i's. So there's a little arithmetic here, so let's just say from the definition of t, I keep saying, okay, so of t of beta I, we get. So this is going to be tau alpha 1 alpha 2. Oh, right. Oh wait, that should be a beta n. Oops, right there, that should be a beta n. Yeah, let me just write it down here. It's a little ugly, but it's not. It's just the fact that sigma applied to B2 can be written in terms of capital T. And so let me just write this down. So it's going to be no, that's a tau alpha 1, tau alpha 1 alpha 2 minus alpha 1 tau alpha 2, parentheses there, and then this will be times t beta 2 plus dot dot dot, and then we'll have tau alpha 1 alpha n minus alpha 1 tau alpha n, but replace this with t of beta n, and then all of this applied to sigma, and that's equal to 0. Now, this is true for all sigma, which forces this mess right here to be the trivial mapping, right? So since this is true for all sigma in G, we conclude that, and I'm just going to write blank square brackets, we can conclude that this function inside the square brackets is equal to the 0 mapping. Okay, fine. But now look at how many t betas we have. We have n minus 1 of them. So by the minimality, we know that the collection t beta 2 up through t beta n has to be linearly independent. If we're going to get 0, then that forces each of these coefficients to be 0. So, oops, and that should be tau of alpha 1. So, by minimality, the collection t beta 2 up through t beta n is linearly independent. And so that tells us then that each of the coefficients here, so let's write this, it'll be tau alpha 1 alpha I minus alpha 1 tau alpha I equals 0 for all I between 2 and n. All right. I mean, this is a very clever proof, but it is a little intricate, and I can easily get lost in this. Okay, so now the next step is that I'm going to do what? I'm going to get one side over to the other. So I'm going to subtract this over, and then I'm going to hit with tau inverse. I guess. Why tau inverse? Made sense last night. Wait, why am I doing tau inverse? Well, okay, let me just do the steps because now I'm not actually seeing what happened here. So then tau alpha 1 alpha I is equal to alpha 1 tau alpha I for, oh, now I see. Okay, so each 2 less than or equal to I less than or equal to n. Now what I'm going to do is I'm going to multiply by alpha inverse and tau inverse of alpha I. And so this will give us, therefore, so we can say therefore, tau alpha 1 tau inverse alpha I is equal to alpha 1 alpha I inverse for each 2 less than or equal to I less than or equal to n. Fine. And then join it together on this side. So this is thus tau alpha 1 alpha I inverse equals alpha 1 alpha I inverse for each I between 2 less than or equal to n. Now, this is true. Remember, we chose tau at random also. This is true for every tau in G. And so what does that tell us? It tells us that alpha 1 times alpha I inverse is in the fixed field of G. So, since this holds for all tau in G, we see that alpha 1 alpha I inverse is an element of phi G for all 2 less than or equal to I less than or equal to n. Okay, so now now I'm going to multiply star. So we're going back to star, and I'll multiply it by alpha 1 inverse. So now multiply equation star by alpha 1 inverse, and so now we're going to get sigma beta 1 plus alpha 1 inverse alpha 2, alpha 1 inverse alpha 2, sigma beta 2 plus dot 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 plus alpha 1 inverse alpha n sigma beta n equal to 0. Once again, this is for all sigma. So this is for all sigma in G. Now, this is true for all sigma. In particular, it's true for the identity. Right? So we can say, in particular, this holds for sigma equal to, I'm going to use a 1 there, the identity in the group. In this case, is the identity mapping. And so, so therefore, beta 1 plus alpha 1 inverse alpha 2 beta 2 plus dot 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 plus alpha 1 inverse alpha n beta n equals 0. And where does alpha 1 alpha I inverse come from? It comes from phi of G. So let's say and each alpha 1 inverse alpha I is in phi of G. So what does that tell us then? So therefore, the collection beta 1 up through beta n is not linearly independent, right? So it's linearly, and I should say is not. How do I want to word this? it is phi g linearly dependent, right? But that's a contradiction. That one's kind of tough. I mean, so there's our contradiction. So that completes the cycle. So that's a tough theorem, and we're going to use it. And if I remember correctly, we use it for the very next theorem, and then we never use it again. Well, I better not say that for sure. But we will definitely need this for the next theorem, which we're going to prove next time because I'm wiped out now, and also I have office hours in just a minute. But the next theorem is going to be a much more Galois theory kind of theorem, right? So this was really just a linear algebra result. Anyways, okay, enough for now. How long did that take me? If you have 40 minutes to prove one theorem. All right.